26F, number 1. Find the area under student's curve with 5 degrees of freedom to the right of 2.02. So if you go to your t-table and you go to 5 degrees of freedom, how much area is to the right of 2.02? On your paper, it's actually 2.015. How much area is to the right? 5%. Does everybody understand how to read that? What if it asked how much area is to the left of negative 1.47? Well, none of the values on the t-table are negative, so what do? You just look at the positive version. And the positive version says there is 10% to the right of 1.47, so there would also be 10% to the left of negative 1.47. Does anybody have trouble reading the t-table? Okay, basically, this is just a chart that gives you the shade norm for the right edge, or it could be the left edge. But the degrees of freedom change the shape of the curve, and the fewer draws you have, the less normal the curve is going to be. So how much is to the left of negative 2.02? 5%. How much is between negative 2.02 and 2.02? 90%. How did you get that? So we found out that there's 5% over here and also 5% over there, so the middle must be 90%. And to the left of 2.02, 95%. Okay. Number 2, the area to the right of 4.02 under the student's curve with 2 degrees of freedom is, so we go to 2 degrees of freedom, we go over to 4.3, 4.03. How much area is there to the right? Is it less than 1%? So with 2 degrees of freedom, the 1% line is 6.96. So no. So it would have to be between 1% and 5. Because 4.02 is between 2.9 and 6.9. Does everybody understand that? Okay. Number 6, a new spectrophotometer is being calibrated. Oh, that's number 5. How about number 6? A long series of measurements on a check weight averages out to 253 micrograms above 10 grams, and the SD is 7 micrograms. The Gauss model is believed to apply with negligible bias. At this point, the balance has to be rebuilt, which may introduce bias as well as changing the SD of the error box. 10 measurements on the check weight using the rebuilt scale show an average of 245 micrograms above 10 grams, and the SD is 9 micrograms. Has bias been introduced, or is this chance variation? Okay, now this is kind of complicated, but it can be simplified into something quite easy. So we believe that the check weight is supposed to be 10 grams. But it turns out it's not actually 10 grams. It's 240, the average of the check weight is 253 micrograms, bigger than 10, right? So it's kind of like 10 point micro would be milli, I think it would be 0.0253. So this is really 10.0253. But we're not going to do that. What are we going to call the middle of our normal curve? Just this. Okay, we'll ignore the 10. And we'll just say, okay, we expect the middle to be 253. Okay? And then we need to rebuild the scale. We rebuild it, and we're worried that we messed something up. So we do 10 measurements. Sorry, this is 253 with an SD of 7. Okay? So 10 measurements on the check weight using the rebuilt scale show an average of 245 above 10 grams with an SD of 9. So we recheck and we get 245 with an SD of 9. Okay. Has bias been introduced, or is this chance variation? What do we need to do? Well, we have to do a t-test. Why a t-test? We only have, what was it, 10 draws? So we have 10 draws. So we have to use a t-test. Whenever you use a t-test, you also have to create the SD plus Y. We have a small number of draws, so the chance that our SD is off is quite large. So we need to inflate our SD a little bit. And the number of draws is the way that we inflate our SD. So we times the SD by the square root of D over D minus 1. Okay, so I'm going to take 9. Well, let me do it this way. The square root of 10 divided by 9 tells me that my SD needs to increase by 5.4%. And that just makes us a little bit more accurate. So I times that by 9, and I get my SD plus is 9.48. Now what do I do? What's next? What's that? I do need to find the p-value, but before I can do that, I have to create my standard error. Okay. How do I create a standard error? I need to find which SE? SEP, SE average, SE for number. The SE for average, because these numbers are averages. So my SE average is going to take my SD plus and divide it by the square root of 10. So divide this by the square root of 10. And I get my SE is 3. Is that what you guys got? Yeah. Okay. Now what? Well, I need to write a null hypothesis. What does the null hypothesis say? The null hypothesis says that 253 is equal to 245. So it's saying that the old measurement is actually the same as the new measurement. So we're going to assume that nothing has changed. What does the alternative hypothesis say? So we're saying that the old is actually bigger than the new. Okay, so to do that, we have to find, it's a z-score, but we're going to use the t-table, so it's actually a t-score. So I take, so here is 245. So 245 minus 253 is 8. And I divide that by 3. and I get 2.6, negative 2.66. That is my t-score. If this was a z-score, what would the answer be? Reject the null or accept the null? Reject, because negative 2.66 is way out there. It's almost highly significant, but it breaks the 1.64 rule. Okay. So I take this negative 2.66 and I'm just going to pretend it's positive. I go to the t-table. How many degrees of freedom am I looking at? I have 10 draws, so my degrees of freedom would be 9. And then I look for 2.66. Where does that land? Between 2.5 and 1. So if my p-value is between 2.5% and 1%, do I reject the null or accept the null? Accept the null. And I say something went wrong when I rebuilt the scale. Right? So is the scale the same as it was before? We think there is a significant difference between the old scale and the new scale. The weight didn't change, right? So something must be wrong with the scale. So what we've basically said is this number is too small compared to this number for the error to be described by chance. Okay? Wait, did I say accept the null? Oh my goodness. Reject the null. I'm sorry. Holy cow, I said that backwards. Your p-value has to be accurate. Yeah. Yep. Oh man, I'm sorry guys. Reject the null, accept the alternative. Right. My explanation was right. Just checking to see if you guys are paying attention. Okay, number 7. Did it give a p-value in the back? Okay. Okay, number 7. Several thousand measurements on a check weight average out to 512 micrograms above a kilogram. The SD is 50. Then the weight is cleaned. The next 100 measurements average out to 508. The SD of 52. Apparently, the weight got 4 micrograms lighter. Or is this chance variation? So we're going to assume that 512 is correct because we've done several thousand measurements. Okay. And so the SD of the original measurements is 50. The weight is cleaned. Then we do another 100 measurements and we get 508. Do I need to do a t-test? Do I need to do a t-test with 100 draws? I could. It's not going to change much because the t-values are really close. So if we end up with right near 5%, maybe we want to switch to a t-test. But unless it's very, very close to being on that borderline, there's really no point. We'll just use a z-test. So we assume that 512 is correct because we've done several thousand measurements. And now we have, we end up with 508, and D is 100, and the SD is 52. Okay. So now, do I need an SD plus? No, because the square root of 100 divided by 99 ends up being less than 1%. So if I did an SD plus, I would make that just a little tiny bit bigger, and watch how small that is. Now it's 52.25, which is not much of a difference. Okay. So A, formulate the null and alternative hypothesis as a statement about a box formula. So we're going to say, for the null, what? We would say the unwashed weight is equal to the washed weight. And the alternative says that the unwashed weight is actually a little bit heavier than the washed weight. Does everybody understand that? Okay. Would you estimate the SD of the box at 50 or 52? Why 50? What does it say in the back? So So the 50 came from the original weight. So we assume that the box hasn't changed and it's 50. And then it said 52 is what? So the SD, oh man, I did that wrong on the last one, didn't I? I used the wrong SD. I'm sorry. Yeah. So those of you watching the video, on that last one, I used the wrong SD. If you have the SD of the box, you always use the SD of the box. Okay? The new SD doesn't matter because the SD has to be related to this number. So the SD you use always needs to be the SD of this number. So this SD of 52 is not important because we're assuming that this is true. If it's not true, then we'll find out later. But for now, we assume that that's true and that nothing has changed. So we're actually going to use the SD of 50. And I totally botched that last one. Sorry. Okay. Would you make a z-test or a t-test? We're right on the border. So 100 could go either way. My recommendation is do a z-test because it's easier. And if the answer is really, really close to 5% or really, really close to 100%, maybe go back and do a t-test and see what happens. But once you get to 100, we use z-tests. What did the back say? Z? Did the weight get lighter? If so, by how much? All right, so we're going to put 508 right here. That gives me -4 divided by my SD of 50 or divided by the square root of 100, which is 5. So -4 over 5 gives me a z-score of -0.8. Do I even need to bother shade norm? Well, actually, if we want a p-value, we better. So what am I going to shade? What am I looking for here? What am I going to do with this? Uh-oh. Any idea? I want to know how much area is over here. If that area is large, then the null is true. If that area is very small, then the null is rejected. So I'm going to shade norm from -5 to -0.8. Can't see much. But the answer is 21%. So, accept the null or reject the null. Let's see if I can get this one right. Accept the null. It's a big percentage. So we accept the null, and accepting the null means what? The weight did not change. Now, let's say the answer was, so did the weight get lighter? No. What if the answer was yes? How much lighter did it get? We don't know. A z-test or a t-test does not tell you how much lighter it became. It just tells you if it did get lighter or not. Okay? If you wanted to figure out what the true weight was, then you would need to do a 95% confidence interval. So z-tests and t-tests do not tell you how much lighter it is. So if I run around and measure a whole bunch of males, and I think that the average male height in the United States is 70 inches, and my sample ends up with 72 inches, and then I do a z-score and I get an area of 3%, I reject the null and say 70 is wrong. What's the true average? We don't know. We just know we're pretty sure it's not 70. Okay? And I could take my sample and do a 2 SE window and create a confidence interval and say, I'm 95% confident that the true average is somewhere in here, but I don't know what that number is. Right? It's somewhere in there. So a z-test or a t-test just tells you, is it the same or has it changed? It doesn't tell you how much it has changed.